Hello, welcome everyone. Actually going to pass you host, Jordan, so you can let people in.
All right, there's already 20 people in here, so we're probably going to see. Does anybody know what I do with my coffee? No.
Awesome. For some reason, oh, you are host, Jordan. Okay, cool. Awesome. Hi, everyone. Welcome, welcome. We're just letting people kind of filter in through the waiting room. Thanks so much for joining us today. We're really excited about this Lunch and Learn. I do realize that a lot of us that are educators are back in buildings, and so lunch is no longer a time we get to take off. So really glad if you were able to make time to be here, see some familiar faces, and also if you're watching from the recording, because you can't make it, glad you're watching. Great. Well, just go ahead and make sure you're on mute for now, but this will be a collaborative time. So, if you have questions later, you're welcome to come off mute. But to get us started, I'm going to go ahead and jump in. And I want to just tell you a little bit about Project Invent. We're hosting this today and kind of just bringing in educators that are interested in this kind of stuff because we have a fellowship that we think you might be interested in. So I'm just going to jump in and tell you a little bit about Project Invent, and then I'll pass it off to Kristin to get to the fun stuff. So you can go to the next slide, Kristin. Cool. So at Project Invent, our mission is to empower every student as an innovative problem solver. I think if you're here today, it's because you're probably connecting students in some way to problem solving, be it building or learning with their hands or making. And that's kind of what we're all about. That's our bread and butter. Go to the next one. But what we do is we really see the value in authentic problems and challenges for students to solve. We make sure students are inventing and coming up with solutions by learning user empathy. And so our students that go through the Project Invent program pair up with someone we call a community partner. And that's someone in their community that faces a unique challenge. In the left-hand picture, and I know if you've been to our sessions before, you've already heard these stories, but just for new folks, this is a team called the Stria team. They were working with Jimmy, who has visual impairment and had been hit by cars twice by veering when he was crossing the road. Using his life and his user interviews with his experience, they designed him a belt that will vibrate to keep him going straight when he's crossing the road. That's just one example of the many things our students invent throughout the year. You can go to the next slide. And the way we get them to that is we take them through 3 phases of our program. The first one is we teach them design thinking. So we teach them, how do you come up with an impactful idea based in having empathy for someone else? How do you come up with a human-centered idea, not just a cool gadget to invent? And then after that, they learn the engineering skills. So they learn how to do cardboard prototyping. They learn how to code with microprocessors. We love Arduino. We love Microbit. That works really great for our program. And then lastly, they learn how to tell that story and make that impact scale. They learn how to come up with a pitch and a business model. And so they're really hitting on so many skills throughout the whole program, not just technology and engineering, though we love that they get that out of what we do. Go to the next slide. And I just want to show you, these are examples of different inventions that students get to by the end of Project Invent. We've got a smart steering wheel to help people not fall asleep at the wheel. We've got a watch that people can wear and use to contact their loved ones if they feel like they're in a dangerous situation. We've got an autonomous shopping cart to help someone in a wheelchair feel more independent at the grocery store. It honestly, every time I see these, blows my mind that our students can get to the end of the year with these products. And I want to let you know that a lot of our students don't start off the year with any tech experience. They're not just coming from the robotics team. Some of them are, but like most of them are starting off with little to no experience with technology, building, design thinking. Next slide. So I just want to plug a few things. That's us. That's what we do. We do that by recruiting teachers like yourself, if you are a teacher, to join our fellowship. And if you want to see some of the inventions from this year, we have a really cool platform because we know demo days can be really long. So we created this really cool platform where you can drop in and out whenever you need. It's not like a Zoom meeting. It's just on a website, live streamed. And we're going to have one more. We've already done 2. They've been incredible on May 16th. So you can just go to, Jordan will drop into the chat the link, demoday.projectevent.org. And you can sign it up, get it put on your calendar. And then, like I said, you don't have to stay for the whole thing. You can drop in and out and just see some of the pitches. Next slide. So I told you a little bit about how we get students to their inventions, but our big method of doing that is by training teachers on the process. That way the students then can empathize with clients, build technologies, and then they present at the end of the year. Next slide, Kristin, sorry. I'm forgetting which slide's coming up next, and that's my fault. Sorry, presenter woes. So we're growing. We're in 50 schools this year, and we're trying to get to be in 100, and we're halfway there in our recruitment process. So right now, recruitment for next year is open. We would love for you to apply if you're a high school educator. If you're not a high school educator, we do have another option for you. You can go to the next slide. So this is the 2 ways you can get involved. If you're an elementary or middle school educator, we partner with the Infosys Foundation to put on our full training for free for public school educators every summer. So the registration is open, and that's actually closing next Friday. So if you want to do that, go ahead and sign up. You'll go to the Infosys website, and it'll talk a lot about this thing called Pathfinders. That's what the Institute is. And then you'll select our course, Project Invent. Program costs for public schools are usually covered. They might have you throw up a donor's choose, but then they'll end up funding it. So don't let that deter you. If you're a high school educator, we want you to apply for our Project Invent Fellowship. We do training in the summer, but then we do program support all year long and help you attend these demo days at the end of the year. So all the links are getting dropped in the chat. We'd love for you to engage with us. If you're into this kind of stuff, we want to make sure that we get you into our community. Okay, I think that's all I had. Let's get to the fun stuff. I'm going to pass it over to Kristin now. We can skip that one. Just move that. There we go. Okay, awesome. All right, Kristin, I'm going to pass it over to you if you want to introduce yourself to the group.
Sure. Hi, everybody. I'm Kristin Burrus. I am a teacher at STEM School Chattanooga, and I've been a Fab Lab teacher for the past 3 years. And so most of my examples and things we're going to talk about today are actually from before I worked in a Fab Lab, because Fab Labs have high-tech prototyping capabilities. We want to talk about low to no-tech prototyping, because that's what most people, most students, especially students if they've been at home this year, that's what they have access to. And so that's what this is really all about. I want to just make sure everybody knows what I'm talking about when I say analog prototyping. Analog prototyping would be prototyping with crafty kind of sticks and tools and glue and scissors and things like that. And we also talk about low, medium, and high fidelity. And really what that means is, like, how well is that prototype going to work? Something with high fidelity might have been made with a plasma cutter or something crazy. Medium fidelity, we're usually talking about laser cutters or 3D printers. But what we're going to focus on today is low fidelity, and that's craft sticks and glue and all of the other fun stuff that we have access to. The thing that I think is greatest about low fidelity prototyping is it gets kids prototyping very quickly. It's not dependent upon them having access to a lot of computers or a lot of different tools. And it's about practical ingenuity, right? So it's about what they can make with what they can find or what you can provide them. So here's a list of tools that may become your new best friends in a low fidelity analog prototyping classroom. I have some examples here. I think that this tool, this cardboard cutter, is probably the greatest $35 I've ever spent in my entire life. It's kind of fun if I turn it on. it makes really cool noises, but it spins, right? And so it cuts through cardboard very quickly, especially when you have thick cardboard boxes like Amazon boxes, which are probably the most accessible boxes that I know I can find around school for kids to cut through, especially if you've ever watched middle school or elementary school students try to cut cardboard with scissors, it's a nightmare. And so I highly, highly recommend the cardboard cutters. And then there's this cool thing called a canary cutter. And I do keep it in a plastic sleeve because it's got a serrated edge, but they can saw through cardboard. It still is, I think, more accurate than trying to cut cardboard with scissors, especially if you have non-straight edges. But with all of these tools, there are some safety considerations, and we're going to talk about that on the next page. The other things that we have are simply eyelets, brads, etc. The thing that you may or may not know from this list is the crocodile. And so if you're a crafter or a scrapbooker, you may have come across the crocodile. This was something I had never seen before 2 years ago. And it can make holes with these two pieces on either side. When you squeeze it, I don't know how great the screen can show. It makes holes of varying sizes. It has a, what I wrote on a different one, what their sizes are, a 3/16 and a 1/8 inch hole. And then you put your eyelets in this part and it will basically crimp the eyelets together. And I can show you an example of a project where I've used those, but it really makes moving parts much, much easier. The low-tech solution is simply using paper brads, and that's these little guys right here. We've all probably seen these before. The one thing about the paper brads that makes them slightly less wonderful than the eyelets is that you then do have the sticking out parts. So you have to kind of deal with that. But then, you know, you gotta love paper straws, you gotta love your craft sticks and all your other analog prototyping stuff. What I didn't write on here are any recycled materials like bottles. I do not recommend recycled cans because they are the sharpest objects on the universe. But so then kids can sort of make anything they want. Here's a little bit of safety information. So I said that I've been a Fab Lab teacher for the past 3 years, but I still had to send more kids to the nurse because of the hot glue gun and box cutters or X-Acto knives. Those are still probably the two most dangerous things in the lab. So depending on the age of your students, definitely go through safety precautions with all of these materials. For instance, the picture of my student there on the right, sitting with the cardboard in his lap as he's using the cardboard cutter. Maybe not ideal, but the one thing about a cardboard cutter, if I can get it back in the screen, is it does have this protective piece here on the bottom. It takes a lot to get your finger in there. I'm not saying they can't, especially don't want to make it kind of a challenge to middle school young men, but that is the only part that's really where you could get to the sharp edge there, but it is remarkably sharp. So you have to talk about those things with your students. So once we start trying to become cardboard engineers, we have to talk about how to get cardboard to do what we want it to do. So the first instinct my students always have is to cut cardboard into 1,000 pieces and use about 12 sticks of hot glue to put it all back together. What is really challenging with that is that that's probably the least effective way to have cardboard be put together. In other words, a folded piece of cardboard is much, much stronger than two pieces that have been cut and then glued back together. So and by the way, I do see a couple things in the chat. Yes, there are some lists at the end. I promise I'll share. I actually got this list from someone else and then recreated it on my board here behind us. And so I do have these examples because students very quickly forget what they can do with cardboard, but there are lots of different joining techniques. Probably the quickest one to learn is simply the slot, where a piece of cardboard has two open ends and you can slide them together. The flange is great if they're using paper towel rolls, because paper towel rolls don't like to stand up straight. So that's simply cut at the bottom to give it some strength. Bending You don't have to necessarily put slits in cardboard to help it bend, but it really helps it bend much, much easier. You can also control the direction of the bend. So you could actually, I've had students build bridges where it bent over because they put slits on top, then they put slits underneath, and then they could bend it back up. So they do have a little bit more control. And then the movable link obviously is put together with a paper brad or an eyelet or something like that. So, and yes, I do have a list with a lot more of those coming up. What I've done with students to make it much more interesting is to come up with design challenges. And one of the things that is really fascinating is to get them to start building games. They love games. And so a reoccurring theme is to build a pinball machine. And you'll notice that, and by the way, the picture on the right is the underside of a pinball machine. I don't know that I added the video. I apologize for that, but they used big giant sticks, PVC pipe, and then the actual flippers are made from cardboard. And it actually worked out to be pretty strong. The joint there was actually made with a little bit of felt so that it could bend. And the cardboard pinball sensors, if you guys have ever gone to instructables.com, if you haven't, I highly, highly recommend it. But there's a whole Instructable about how to make sensors with what you're looking at there is it's a type of, it's not copper tape, but it's a type of copper tape. I think it's called make tape, where as the steel ball rolls across, it actually completes a circuit, and it can be used to make lights go off or sensors go off or something that gets the kids really excited. So that can be used in a pinball machine, or it can be used for other ideas as well. So these are some of my students when by the way, what I did before I was the Fab Lab teacher is I was 7th grade science for like 20 years. And so that's where most of my examples come from. But we used cardboard to make Rube Goldberg machines, to make windmills, that's the top right one, and to make animal habitats. And so what makes this a little higher fidelity, I don't know if you can tell, but by using things like canary cutters and cardboard cutters, the lines became sharper. The kids could have a lot more control over what it was they were cutting, and they could actually measure instead of just kind of going nuts with some scissors. And so those are some examples of cool stuff. And you'll notice whenever we analog prototype, it's not just cardboard. There's lots and lots of rubber bands involved in some of the others examples as well. And then in this particular example, the kids were making earthquake resistant buildings. And to give this an actual design challenge, a colleague and myself found plans online to build ourselves an earthquake machine. And so if you look at the bottom left-hand corner, you'll see there's a drill connected to a series of levers that basically shakes the heck out of this table. And the kids had to build a building that could survive for, I think it was 30 seconds. And because it's hilarious, I hope you can hear it. I want to play a video for you guys. So there's lots of excitement when you can build a design challenge around something that has to survive. So on different years, you may notice that at some point these were cardboard buildings, at some point these were popsicle buildings, and then the last iteration is that I let them choose their materials. In fact, with that particular design challenge, they were given a budget, and popsicle sticks had a price, cardboard had a price, and then they had to figure out how they could build a house or a building with a certain amount of materials that could survive the earthquake. So that was pretty fun. Oh, sorry, playing again. How do I get it to go to the next slide? There we go. Some of the other things about cardboard engineering that is, I think, one of its benefits is that it's part of the iterative design. In other words, if students are going to make something that has a higher fidelity final product, they start with cardboard before they move on to other materials, mostly as just a way to test their design, because they need to go through the process. So what we usually have kids do is start with a small analog fabricated model. And even before that, a sketch. You can see a sketch in the upper right-hand corner. That's usually where I start with kids first. Get their idea, make some measurements, do some, some thinking about it, then build it with whatever you can find around the classroom or around your house if they happen to be at home. And then final product could be digitally fabricated, or it could just have a higher fidelity. If you have access to a 3D printer, I think this group's final little fish was a 3D printed fish after building it in Tinkercad. The 3 axes in the middle, that was actually a social studies class. They were studying, I worked on this with another teacher. So what would it be called in 7th grade? I guess not pre-civilizations, early human civilizations, something like that. But all the kids thought it was great because, well, the tools of the early humans were all weapons. And so they really totally got into that. But anyway, so they had to build it as they were part of the cardboard or the paper age was the first age. And that was supposed to be kind of like the Stone Age. Then the cardboard age was supposed to be the next age. And then the Bronze Age would be the digital fabrication age. I actually have that whole thing. If anyone is interested in teaching social studies, I can share that lesson plan with you.
The far right picture, Kristin?
Oh, the middle school social science. Oh, social science. That should have just said science. That is a fish and it had to float. So that was, those are connects and straws. And that top one, is that the one you're talking about? The one that has a little tiny fish? Or are you talking about these 3 at the bottom? The 3 at the bottom are a high school STEM project, and they were actually creating a packing system for a trucking company, a local trucking company, to see if they could pack their trucks better. And so they made their final model out of acrylic so that you could see through it. And then they 3D printed their cargo because it was really all about how they could pack the inside, but they still started with cardboard and then eventually foam and up into their acrylic. Oh, I think the Kinco, this paragraph here at the bottom explains the high school STEM, their project description. Did I answer that question?
Yes, I think you got it.
Okay, thanks. Sorry. So anyway, so those are just some different examples, and you can all obviously tell my previous students, my 7th graders, in the top 2 pictures, and then what can happen at a high school level, even with analog prototyping. So, and what you can't see, I wish you could see it in this small scale fabricated model, the foam version. They actually had foam squares inside. They could take the top off, and they were still working on how to maximize the load, how to keep it balanced, and how to pack effectively. Then I guess once kids are making things with cardboard, we began adding electronics. And the very first electronics that I added with my students were fun with Spheros. If you've never played with a Sphero, it's a little round robot. And so the students used their cardboard engineering to create mazes, and then they had to program the robot to make it through the maze. And you can see in the left picture, one of my 7th graders is sharing their maze with 4th graders, I believe. It was 3rd or 4th grade. And they were having to drive the Spheros through the maze, and then they timed them to see who could get through the maze the fastest. Another design project that we did with 7th grade science was building, they called them pirate ships, but they kind of look like ducks. But these are floating objects with Spheros as the way that they moved. In other words, the Sphero sat in the middle and could actually drive the boat around. The front of the boat had a pin, and the back of the boat had a balloon, and the job was to pop the other ship's balloon. And that was their design challenge. And so we were studying buoyancy and other physical science concepts. And this was really got kids interested in thinking about how to design something that floats and moves. And then they just really enjoyed attacking each other's ships because that's what they like to do. So anyway, so that's what's happening there. Where things can get really, really fun, and Kelly actually talked about this earlier, is adding Arduinos and microbits to your analog prototyped designs. So I guess for some folks, like if you've ever played with a servo is in the bottom corner. It can be programmed to, it goes from 0 to 180. So it's basically a lever that goes back and forth. But when you attach it to a popsicle stick, it can sort of look like a horse is galloping. And there are just tons and tons of examples. And I want to share with you, it's about 3 minutes. I hope that's okay. This microbit virtual parade. It even has music. It's very exciting. But this was a Twitter challenge for folks with microbits to create a critter that could be part of the virtual parade. And so let me go ahead and click play on that, and then we'll talk more about it. We're going to go a little faster. Okay, so I'm going to go ahead and stop it. By the way, if you want to see more, and if you want to get in touch with any of the people who participated in the Microbit Virtual Parade, I'm pretty sure it's just hashtag Microbit Virtual Parade on Twitter, and they are still there. And a lot of these folks work with microbit educators, and they're called Microbit Champions, and they would love to share their designs and all the cool stuff that they've done with their students. I did see a question about time. So time is one of those things that it just kind of depends on your students, right? And how much scaffolding you give them. But pretty much in most of the examples, this was a much more than a classroom project. This would have lasted during the entire unit that we were studying. One of the things that I always tried to do is not leave the project or the fun thing till the end, but we would begin our project at the beginning of a unit, and we would work on it on and off throughout the entire unit. So for instance, when we were doing physical science with the boats, that was at least a 3-week unit, and kids got to work on it on and off during that unit for maybe 4 class periods. And a lot came in at lunch because they wanted to win. They wanted to beat up the other boats, plus the days of actual experimenting. So it can take a bit of time. But what I found is that those are the things kids remember forever, and that the learning is really worth the project, or the problem-based learning unit. Really adds the depth that they need for the concepts. But anyway, so here is an example. This is probably an elementary example of making a cardboard animal. I have my example. He's cute, but his little trunk moves. But it's a very simple example of creating something out of cardboard. You'll notice this is the world's tiniest, skinniest cardboard. So actually making this, I used scissors. It wound up being too small to use the cardboard cutters with the details. And you'll see my design in the middle. All I can say is play to your strengths. I am not the kind of person who sketches well. So his legs were not even, and he did not stand up correctly. I had to do lots of adjusting once it was made out of cardboard. I can laugh at myself. My students used to think it was hysterical when I would draw on the board. But anyway, it does take some effort to get the little guy to stand up on his own. But so the kind of things that we might do with the cardboard animals would be, obviously there's a lot of science connections. They could make a zoo. They could create the habitats where the animals lived. They could do some research about what the animals can do. Obviously, if you're interested in robotics, they could move the animals. I don't know if you saw that caterpillar at the beginning that scrunched and actually crawled across during the microbit parade. And then here in Tennessee, we call it ELA, but English Language Arts. Kids could write stories or poems, and this could kind of be their muse as they're doing those other activities. And there's a link here, and I would love to share it. When I say play to your strengths, I found this on Pinterest, looking up horse patterns. So if you are not the kind of person that sketches well, I highly recommend you use those resources out there in the world. I was working on my little horse today. I didn't get all the pieces together, but using someone's pattern, it's amazing. He stands up quite nicely because he's even and symmetrical and actually kind of works well. And I did want to share with this, when I say cardboard engineering, we use foam as often as anything else. That's probably because there's a company here in town that gives us scrap pieces for free. So if you have any way to reach out to sign companies, or this particular company is called West Rock. I got to be honest, I don't really know what they do, but I taught one of the student of someone who worked there, and when they offered us foam, we're talking pallets of 2 by 5 foot foam. So I have a lot of it. So we use foam all the time, but I do know it's expensive if you're trying to buy it. So the idea here is not to spend a bunch of money, but to use things that you can find. But I just wanted to share, do find other things on the internet when you can. Here's one of my favorite cardboard engineering challenges. And this it can take on many different iterations. But the idea is to build a tiny table out of cardboard. And I've done this different ways with different students. In some cases, I say, no, you can't use any glue or any masking tape at all. You have to fold it, bend it, and make it as strong as you can. Other times, I'm for it, here's some tape. But this was a really great experiment that we did with students. And it was at the beginning of science, when they were really just talking about the design, the engineering design process. And so it was, how can they make a plan test their plan, change their plan, and figure out, how to make it better. I put in the additional teacher info, these kids made tables that were cardboard tables that were so ridiculously strong. We had to borrow a few of the weights from the end of a barbell, to the point where it did not crush the little tables. We just stopped because I was worried it was going to fall over on somebody's foot. So that was quite an experiment. It was way fun. The kids really liked it. They liked the competitiveness, some of them, of it. And then they got to, anyway, they got pretty much free range. I've seen some folks, if you look at the picture at the top, this is actually from a picture I found on the internet. I didn't have any pictures of these tables. I couldn't find them, but I've seen it where it was newspaper that had to be rolled up. That's the picture at the top. And then, but the way I did it is we just had boxes and boxes to cut up and use to make their tables. I guess I want to kind of pause to see if anybody has any questions or I see a couple. I didn't, something about the foam. Oh, I can't find it. Is it foam or corrugated plastic? It's actually, I think it's called craft foam. It's foamy on the inside and kind of like a paper on the outside. It's not actually corrugated plastic. The corrugated plastic is, I agree with your comment, it is not easy to cut. However, I have a feeling that these would cut through the corrugated plastic pretty well. But that still might be really challenging. But this is the foam. You can buy this foam. If you see in the middle, it's kind of different from the sides to the middle. So it's like paper squished in with foam. I'm sure it has a better name than that. To reduce time, would you have the parts pre-cut and let the kids assemble? It completely depends on what you want to do with the kids, right? So I got to be honest, I cut, like, I don't know if you guys saw for this one, I actually cut his body with a laser just to save time. And then it wound up not saving time at all because the pattern didn't have the little cutouts for the pattern weren't the same thickness as my foam. So that's one thing I would recommend if you're having kids draw their own patterns. Think about the thickness of what it is they're putting together when they do slots, because that makes a huge difference. So so having the right size slots will reduce time. So I guess, it just depends. Like if there's something to be said about the making of it that is really nice for students to be part of that process. But in my class, making was the reason why we did it. And so I never pre-cut anything for them. But you may have a different reason for making. If you wanted to focus on the coding, yes, but there's going to be downtime, especially if they're in groups. And I don't know, I felt like the making was the part that they were really proud of too, especially if it's completely open-ended, right? I very rarely gave students a project with a template. Like this is kind of a starting point and for kids that don't know how to get started, maybe. But or as just my example of, hey, you can make an animal, but really I like kids to make their own stuff and not just recreate something that I've pre-planned. Anything else? Cool. I think this is the page that has all the information. And so I believe if I actually click on this, control copy, this is the whole presentation. And I believe that I've made this. Maybe somebody can click on it and see if I made it so that anyone can view. If not, I can change my settings so that you can get there. Yay. Okay, so you can get there. Good. So you can click on all the links, including my sad little, where is it? my sad little elephant is a download. I do not recommend you using this with students. It was a nightmare, just because I can't draw. But I do want to share this with you. So if you, this book, it's called Super Arduino, especially if you're getting started with kids and microcontrollers. This book has a lot of really interesting information about how to connect, for instance, piano wire to a servo to make the tail of this shark flow or swim in the air. But it's a lot of really great tips. It also has some tips on how to code an Arduino, but specifically around making projects. I didn't put it on here, but one of my favorite books in the entire world is Invent to Learn by Steger and Martinez. Oh, I hope I'm spelling it right. Oops. But if you're just getting started in making, Invent to Learn has a bazillion great ideas. I would call it the maker's Bible for getting kids to make things in class, from low fidelity to high fidelity, which is really kind of awesome. If I clicked on, is it going to go to the right page? Those are this one. Can you guys still see that screen? I think you can. So this is the person's, this is how I made my board, is what I'm trying to say. This was the inspiration for this board, of all the different cardboard techniques and kind of what they were called. It has more than I made. For instance, I didn't put a smooth joint up there because when you look at the board, there's nothing to see on a smooth point. It just looks, well, anyway. So, but I usually have a couple of these out and about. If you were creating maybe a micro-credential or a badging system for students, you might get them to be able, if they are becoming cardboard engineers, maybe they have to do 5 from the left and 5 from the right, and make their own different cardboard joints and folding techniques, and put those into a project if you're interested in badging or something like that with your students. But these are pretty great prototype or examples. I'm trying to think what else. Oh, if you're interested more in the making a pinball machine, oh, what is this? It is not unsafe. I've been to Kane's Arcade before. If you guys are all in school, our district is really, protective over where we go. But if you've never been to this website, Kane's Arcade, it was about a young man who built a cardboard arcade in his dad's garage, or his business's garage. And it is a fascinating video, well worth sharing with your students if you're going to have them make games with cardboard. It's very inspirational. It makes a heck of a kickoff event. And so I definitely advocate for Kane's Arcade. He's actually a grown-up now, and you can look up what he's doing now. It's pretty awesome. Okay, so I feel like I should stop yapping. Is there anything else that people have questions or something I can go back to? I could have missed things in the chat.
Thanks for all of that, Kristin. It was super helpful. We've got 2 more minutes left, so if you want to hang out and ask some more questions, feel free. If not, thank you so much for coming. I know we'll hang out for about a few more minutes till the time to answer questions. But thank you so much, and I think you have a few questions in there, Kristin.
Sure. I was answering the cardboard cutter. It's some people call it a zip snip, but it's by Works. This one, it's my favorite. I know there's one that kind of does this really fast. I didn't like that. I personally didn't like it. I'm sure it works fine for other people. But I will say this is about $35 to $40. It used to cost $30 and now it costs more. Maybe there's too many of us out there that like them and they went up in price a little bit. But for a classroom of ideally 25 kids, I only had 4, and they would have to go to the cardboard cutting station, but we could have a lot more of the canary cutters. These are definitely more cost effective. So I would have these for every group, even if they were in groups of 2, and then I would have maybe 4 cardboard cutters. And then most everything else is the crocodiles aren't, I would say if you're thinking about a classroom budget, you don't have to have the crocodiles. The one thing I do like about them is that, I don't know if you can see the distance here, is that you can actually get cardboard in there. Unlike a lot of those 1-hole punches, you can't get the cardboard in to make the punch, and then it sticks and it can't come out, and it's a big giant pain. But even just 1 or 2 of these per classroom and it would work fine. And I still have students use these and the paper brads, even if we're not making eyelets. Eyelets are generally not available for students until they've done 1 set of prototyping, right? Show me that you've made it the right size, show me that it works, and then I'll give you the eyelets and you can kind of make it permanent. But the eyelets were great for popsicle sticks too, just kind of as an FYI. Oh, do I have reflection planning docs? Boy, I have a ton. It's all about pre-planning. I can, I don't know if I can find those on my computer in the next like 20 seconds, but
what we can do, Kristin, is we'll send out the recording tomorrow, and any links that people have asked for, if you can just email them over to me, we'll include that in that email to everybody.
Great, because there's different kinds. It kind of depends on if we're doing the engineering design process or design thinking, or if it's just rapid prototyping. I kind of have 3 go-tos depending on the type of project. And then the reflection, if you've ever heard of Scrum, it actually was for coders and in industry, but it's what do we need to do? What am I going to do today? And then you divide up what the different people on a team are going to do for those. So that's kind of, and then at the end, they have to reflect on how they did, how'd they change it. If they had $100 in 10 more days, what would they do differently to their final design? Oh, do I have brilliant ideas for not shared materials? No. I mean, I guess, can you rotate things in and out on different days and maybe put them through a dishwasher on different days and bring them back to school? I know that, a lot of these things can go through a dishwasher. I think it would be totally fine, or some wet wipes. I'm sorry, I've been in a school that hasn't been that stringent, I guess. We're all about the masks and we're all about social distancing. But we have been able to share things as long as we clean between classes. So sorry, I don't have a great idea, but I bet some of the rest of you guys do if you want to share.
Awesome. Well, we're actually a little over time, so we're going to go ahead and close out the room. But this was amazing, Kristin. I've already seen it in the chat. A lot of people got some value out of it. Like I said, we'll send the recording out and all of the links tomorrow. And so, Kristin, you can just send those over to me and Jordan, and we'll make sure that gets put in the email. Thanks, everyone, for coming. And we really appreciate it. Have a good rest of your day.
Thanks, everybody. Bye. Good luck.